All right, the question is simple. What do you do with a triangle that is not a right triangle? Well, if a triangle is not a right triangle, then it is either an acute triangle or an obtuse triangle, right? By default. So how do we solve a triangle that is acute or obtuse? What do you do with that? So let's talk about that today. So if you have an acute triangle, let's say this one, and the angles are alpha, beta, gamma. Gamma just looks like a alpha on its head. Okay, so I usually write my gammas like this. Some people pinch it together and write it like that. So you can write gamma either way. Okay? But it's no longer 90, see, so you need to have a variable for it. In this diagram, maybe alpha is 50 degrees, beta is 60 degrees, gamma might be 70 degrees, that's 180 degrees total. All angles less than 90. Acute triangle, right? Acute triangle. And if you have an obtuse triangle, one angle is supposed to be bigger than 90. I'm guessing it's beta up there. A little bit small looking, maybe I should have made it bigger. But let's say alpha is 50 degrees, beta is 100 degrees, gamma, we only have 30 degrees left in the triangle. So something like this. Maybe I should have made the alpha the 30 and the gamma the 50. Anyway, the point is you have one angle larger than 90. Both of these triangles cannot be solved with SOHCAHTOA. There's no hypotenuse, right? You can't use Pythagorean theorem. There's no hypotenuse. So what do you do?
Would tangents or?
No. Tangent is opposite leg over adjacent leg, and therefore legs need to be present, and we don't have legs here. Or sides. So we just can't use any of the stuff from yesterday, really. Okay, let's just talk about how do we even know we can solve a triangle? In other words, how do you even know that a triangle has specific lengths and sides? So let's just spend a couple minutes on that. Let's say that you're given a triangle, just like the one I just gave you, and I said, hey look, this triangle here has angles 50, 60, and 70. Find the sides. That's a trick question, because watch this triangle. You can stretch this thing really big, really small. The angles don't change, right? How in the world can you find the sides if all you know are the angles? That is impossible. This is why there's no AAA congruence rule. There are all sorts of triangles throughout the universe with angles 50, 60, and 70, and many of them are not the same size. Same shape, not the same size. But if you're given that, let's say, alpha is 10, that changes the game. Okay? If alpha is 10 centimeters long, all of a sudden this triangle becomes unique. And there is all the other triangles in the universe with angles 50, 60, and 70 with a side length alpha 10 or A10, they're all exactly the same size. Okay? And the same is true for the obtuse case, of course. So what we're saying is, recall that a triangle with three givens in the form of ASA or AAS is congruent to any other triangle with those same three givens. So if someone says, hey, I've got a triangle that's 50 degrees and 60 degrees and 70 degrees and the shortest side is 10, you can say, well, I've got that triangle too. You can be sure that those triangles are exactly the same. Same area, same perimeters, same exact thing. Maybe they have a different name. One's ABC and the other triangle XYZ or something. Okay, so congruency. Another way to say that two triangles with the same givens are congruent is to say that one triangle with three givens is unique. Okay? Unique. So we kind of stopped teaching this. I'm pretty sure your geometry teacher didn't use this word very much, but it's a really important word in mathematics. All it's saying is, listen, once this is 10 and these are all 50, 60, and 70, this triangle is now unique. There's no other triangle with 50, 67 and shortest side 10 that is different from that. They're all the same triangle. It's unique. Okay? And in mathematics, anytime something is unique and there's enough info, you can solve it. Okay, so I said it. We should be able to solve any triangle where the angles are known and one side is given. Okay? But how? Well, to solve a triangle where you're given two angles and one side, you have to use, or can use, the law of sines. Okay, does anybody remember the law of sines offhand? You can actually quote it from memory. Does anybody remember it? It's a really simple law. I'll give you a hint. It's an extended proportion, so it looks like this. It's 3 fractions, one after the other.
Oh, but is it sine A over A is equal to sine B over B, which is equal to sine C over C?
You got it. So sine alpha over A equals sine beta over B equals sine gamma over C is the law. It's a really simple law. In fact, most people have no trouble memorizing this one. Tomorrow we'll do another law called the law of cosines, and that was a little harder to remember. Yeah, that one has a quadratic look to it. Almost looks like the Pythagorean theorem a little bit. So listen, we need to prove this before we use it. Okay? So, how do you prove it? Did everyone write down the law? I'm just going to change pages here.
Could you just take 2 parts, like sine A over A equals sine B over B, and prove that?
That's exactly what we're going to do. So I'm going to draw a picture of a non-right triangle, and I'm going to break it into 2 right triangles and show you why this law is true. Can I move the page? Okay. So here's just a random scalene triangle. I want it to be acute, but I don't necessarily want it to look equilateral. So how about something like that maybe? And I'm going to need 2 of these actually. So let me clone that thing. Okay, so this is going to be side A, B, and C, which gives us angles alpha at the top. Remember, you have to put the angle alpha across from side A. Beta would be this corner. And gamma is the corner across from angle C. All right, so let me label the other triangle too real quick. Okay, so there's our drawing. And you may not use Pythagorean theorem, you can't use SOHCAHTOA here. So what I would suggest is we draw like an altitude right here maybe. There are 3 altitudes I could draw, but I'll just draw this one. I'll draw this altitude here. Altitudes always go from the one corner to the opposite side in a right angle fashion. So that's called an altitude. And what happened is I just put this into 2 right triangles, right? So let's just color code everything. So this will be green. And the one next to it blue. Those are right triangles. If you look at the green triangle, actually let's give this a name. Why don't we call this H for height? Okay? Isn't it true that in the green triangle, sine of alpha is H over C? Because opposite of hypotenuse in this green right triangle would be H, which is across from alpha, divided by the hypotenuse C. Okay? And in the blue triangle, we could write sine of gamma equals H over A. See? Okay, now let's look at our other drawing. In our other drawing, I'm going to draw my altitude this way. From angle gamma to side C, like that. And I'll call this capital H, just for lack of a better name. Again, I get 2 triangles. Let's call this one the green one, like that. And then we got this blue one right here. So I'm basically repeating what I did in the first picture, only this time it's an upper and lower triangle oriented like this. Okay, let's try and write down 2 similar statements to before, like what we did before. So look at the green one. It would be sine of alpha equals H over B. And in the blue triangle, it would be sine of beta equals H over A. Hypotenuse over, I'm sorry, opposite over hypotenuse. Okay, the rest is simple algebra. Going back to my first picture, if both of these contain H, then we should be able to link them together. So I'm going to write this as H equals C sine alpha, and I'm going to write this one as H equals A sine gamma. Well, if H is C sine alpha and H is also A sine gamma, then C sine alpha is equal to A sine gamma, see? And if you sort of uncross multiply that, you know, put it into a proportional look, it looks like this. Sine alpha over A equals sine gamma over C. Sine gamma over C. If we come over here to this other pair of fractions, I can write capital H as B sine alpha and capital H as A sine beta. But again, these should be equal, so you can write B sine alpha equals A sine beta, and in proportional form, or in proportion form, it would look like this. Sine alpha over A equals sine beta over B. So I thought sine alpha over A was equal to sine gamma over C over here on the left. Well, sine alpha over A is equal to both sine beta over B and sine gamma over C. And there's your law of sines. By the transitive property, then sine of beta over B would equal sine of alpha, or sine of gamma over C. It's actually really not a very hard proof. As far as proofs go, it's actually a pretty simple one. The Pythagorean theorem is harder to prove than that. Really. Unless you go with those, some of those silly visual proofs that they have. Okay, so let's just assume this now to be true. We will use this law as often as we can. Here's the question, when can we use it? When can we use this law? Can we use it on a right triangle?
Yeah.
You actually can. You actually don't need SOHCAHTOA anymore. This is a more powerful tool. This will override SOHCAHTOA. Right? This is the Pythagorean theorem to solve any right triangle.
Does it matter? Do you have to have angle, angle, side, and angle, side, angle, or can you just have any two angles or any two sides?
This is the question. How far can we take this thing? Because this is a great little tool. It's really easy to memorize. It's more powerful than your SOHCAHTOA rule. Can it solve right triangles? But can it solve any triangle? The answer is no. So, not efficiently anyway.
Because there could be two answers in one angle.
Yeah, there's a lot of things about the law of sines we have to be careful about, but know that it's a very powerful tool and it's most effective when you're given two angles, okay? Like in this problem here, it says solve the triangle if A equals 2, alpha and beta are 35 degrees, 84 degrees. See how they're giving us two angles? Law of sines is the way to go, okay? If you sketch this out, if you want to sketch, you don't have to, but if you sketch it out, you'll see it looks like this. Here's alpha, here's beta, here's gamma, here's A, here's B, here's C. They're telling us that A is 2. They're telling us that alpha is 35 degrees. They're telling us beta is 84 degrees. Right? This is what we call an angle side scenario. Right? Two angles, but the side that they gave us is not in between them. This is an AAS scenario. Law of sine works great. Law of sines works great on this. Watch. Just set it up. Sine of 35 degrees over 2 equals sine of 84 degrees over B equals sine of the third angle over C. Well, the third angle is easy enough to find. The third angle is just going to be 180 minus 35 minus 84. So what is 180 minus 119? 61. So I had to find that, but it wasn't hard. You've got everything you need to solve here. Typically what you do is you try to understand that this is really 3 equations in one, is what it is. It's sine alpha over A equals sine beta over B, but it's also sine beta over B equals sine gamma over C. It's also sine alpha over A equals sine gamma over C. So it's really 3 equations in one. I'm just going to take the first 2 fractions and cross multiply. So this is probably where it feels familiar to you, if you've done this before. So just trying to isolate B, you'd cross multiply, and then you would divide, and it just turns out that you're going to have this. That 2 is going to get multiplied over to the sine 84. You're going to have a b sine 35 on the other side, but you can divide by sine 35. I did that in one step to isolate b. Mentally, I did 2 things. If you need to show more work, that's fine, but it's time to grab the calculator. Be careful when you're typing this. You need to close the parentheses, especially on that 84. Okay, so let's see what b is. That's one of our 3 unknowns, b. And it's a side, so we need nearest 100th. What is it?
3.47.
There it is. Okay? Now, if you want to find something else, say side C or whatever, just pick a different pair of fractions. I recommend you pick the sine 35 over 2, which is your first fraction, and the sine 61 over C. I would not use the 3.47 if I were you, because it's already rounded, so we don't want to probably use it in our work. Let's go back to the drawing board and use the givens as much as possible. So let's use this fraction and the third fraction, and let's cross multiply that one. So isolating C, we get 2 sine 61 over sine 35. All right, so what does that give us? 3.05. Okay, so I thought we were supposed to find 3 things. Well, remember we found the 61 degrees right at the beginning? That counts as part of your solution. So the final answer for this problem is alpha is 35, A is 2, beta is 84 degrees, B we found is 3.47, gamma we actually found it was 61, and little c was 3.05. Be careful not to put degrees on anything but angles. 3 givens, 3 answers. Anything that's approximate, you should use the squiggly equals sign. So let me make sure I have a squiggly equals sign on some of this stuff. And let's just do a real quick self-check. It should be true that alpha, since it is the smallest angle, should produce the smallest side A. Say alpha is only 35 degrees, beta and gamma are larger than that. So it turns out that side A is the shortest. That makes sense. A is only 2, B is over 3, and so is C. Also check real quick, where's my largest angle here? 35, 84, or 61, which one? 84. And beta is, the Greek letter B. So is B the longest of the 3 sides? Yes. 3.47? It is. Okay, so just do a quick self-check with that, just in case. Make sure you got everything typed in properly. All right, let's go on to ask about limitations of this law. So we said it's really good for that AAS problem we just did. It's also really good for ASA. It is mainly used for AAS and ASA. Okay? It is not good for SAS and SSS type problems. It is not useful. You might say, why is it not useful? It's just hard to solve. Let's say that you were given a triangle like this, where A is 3 and B is 4, and this is angle gamma here. Let's say that that's 10 degrees. Once you set up your law, it's going to look like this. It's going to be sine of alpha over 3 equals equals sine of beta over 4 equals sine of 10 degrees over c. There's just too many unknowns here. No matter which two fractions you pick to try and cross multiply, you find yourself in a very frustrating situation. And you run around in loops and circles with this. It's just not good for SAS. It's also not good for SSS. Let's say you have sides 3, 4, and 2.5 or something. How are you going to solve this? You know, sine alpha over 3 equals sine beta over 4 equals sine gamma over 2.5. Every time you pick two fractions to cross multiply, you find yourself dealing with two variables. That's not good. The best way to handle these two problems, SAS and SSS, is to use the law of cosines. So in other words, this is not the right tool for the job. Law of sines is great for AAS, AS, and ASA. So is that all it's good for? It can also solve one other kind, the SSA. The SSA. Okay? The law of sines can solve a triangle with givens in the form SSA. You might say, wait a minute. What do you mean SSA? That's not one of the rules in geometry. It's not a uniqueness theorem, and it's not a congruence theorem, but you can certainly have a triangle that has sides 5, 11, and a 30-degree angle right here. There's nothing forbidden about this. So what do we mean there's no SSA rule? What does that mean? It just means that this triangle, under certain conditions, will not even have a solution. And in other conditions, it will have one solution. And in some cases, it could even have two solutions. It all depends basically on that angle right there. Okay, let me try and convince you. Let's say that I gave you, three chopsticks, okay? And one of them was length 10, and one of them was length 5, which is half of 10, of course. And I just gave you a third one, a really long one. I said, just take the third one home, and you can cut it to however long you need. Just make it however long you need it to be. But I really want it to form a 30-degree angle with the 10. So you take this home, and you're going to make a triangle for me, like a little project, okay? So you take your third chopstick, and you stick it on here like this, like that, and you make sure that this is a nice 30-degree angle like I asked. And then you cut your chopstick to size. Okay? Well, it turns out that what you just created is a right triangle. Okay? Isn't sine of 30 1/2? Right then. That must be a 90-degree angle. Right. But what if you had what if the instructions had been given where you had to make this a 6? So maybe I gave you a slightly longer chopstick. So let me erase this now. So you're given a 10 and, or actually let's do this. Let's make it a 4. Let's say I gave you a 10 and a 4. And I said, okay, now go home, take this third chopstick. You can cut it to whatever you need, but you got to make it a 30-degree angle with the 10. So you bring the chopstick over here. You make a 30-degree angle right here, like I said. You know what? You're not going to be able to make a triangle. The little 4 segment is too short to reach. It can't reach. We've got a problem. And you're not allowed to squish this angle. I said it had to be 30. So now the 4 doesn't quite reach. It's not long enough to reach across this gap. Shoot. Okay, well, what if I had given you instructions that this was supposed to be a 6? So now it's a little longer. Same instructions. You got to make that 30-degree angle. So you bring your chopstick over here, your third chopstick, you set it on here like this. And you try really hard to make sure this is 30 degrees. Maybe you have a protractor at home. Well, it turns out there are two possible triangles you can construct. The one you see here in black, or the one you see here in red. There's two places you could put the 6th chopstick. It can go here or here. There's two possibilities. Okay, this is real. I'm not kidding about this. The 10, the 5, the 6, all that for, you either get a triangle, or you get no triangle, or you get two triangles. See the problem? So SSA is just simply not a uniqueness theorem. It's not forbidden for any reason. It's just, it's not going to give us a unique solution every time. We can actually get 0, 1, or even 2 solutions to an SSA scenario. Okay? So I think we should do an example of a 0 solution case, a 1 solution case, and a 2 solution case. The math is not hard. Here's my first one. Solve the triangle if A is 10, B is 27, and beta is 31. Okay, you do not need to draw a picture. All you need to do is set up the law. Sine of alpha over 10 equals sine of beta, which is 31, over 27 equals sine of gamma over c. That third fraction, I don't know anything about that third fraction. I don't know the gamma or the c. But the first two fractions, I can cross multiply these. I get 27 sine alpha equals 10 sine 31. And then if I divide by 27, I get this. Okay, let's get the calculator out and try and find 10 sine 31 over 27. So let me get my calculator out here too. Okay, I get basically I'm getting sine alpha equals 0.1908. How do you get alpha? What button do you use? The inverse sine button, correct? Well, solve will give you multiple answers on this problem. So alpha, your calculator will say is 11 degrees. I mean, I tried to round it to the nearest tenth, and it was 10.9968. So that's 11 degrees. And the thing about this is there's another possible answer, right? The supplement of 11 should also have the same sine value. Remember we said that sine of 180 minus theta is also the same as sine of theta? So you would put or 180 minus 11. In other words, 169 is another possible answer for alpha if it fits in the triangle. Okay? Now, in our triangle, we had originally that beta was 31 degrees. Right? Since beta was 31 degrees to begin with, I can understand having an 11 degree angle and a 31 degree angle in a triangle. I still got plenty of room left over for my third angle. But I can't understand how we can have a 31 degree angle and a 169 degree angle. That's already 200 degrees. I don't have any room left over for a third angle. See? So at this point, after writing the 169, I'm going to cross it out, knowing that it is not meaningful, and I'm going to go with alpha equals 11. Now, if that angle had fit in the triangle, I would keep it. Okay? But I'm not keeping it. It doesn't fit. Doesn't fit in the triangle. I've already got 31 degrees up here, see? Okay, let's move on then. Sine of alpha gave us 11 degrees there. So what we now know is that alpha is 11. But remember, beta was 31. So I think we can find gamma right now. Gamma is just going to be 180 minus 11 minus 31. So what's that? 138. Okay, so here's your law of sines now. You now know that this is sine 11 over 10, sine 31 over 27, and sine, oops, not degrees, just 27, over sine 138 over c. Now you can go ahead and solve for c. Just pick the second and third fraction or the first and third fraction. I'll pick these two. So C is going to be 27 sine 138 divided by sine 31. That's a 27, not a 2.7. Okay, so what is C? What does C turn out to be there? Let's see, 27 sine 138, all divided by sine 31. I'm getting 35.08. And that was my last unknown. So how many solutions did I get in the end? 1. 3 answers means 1 solution. Tomorrow we'll do the case where we have 2 solutions and even no solutions. I'm not assigning any 7.2 tonight because you're still working on 7.1, but we got a good head start on the lesson. Bring your book to class tomorrow.